Okay, the topic today is building models for GIS analysis using ArcGIS. This information can be found in Moodle. For this particular course, it comes after our solving spatial problems using GIS Module 6, and we're working down here in Module 7. There is an Esri training course that goes with this module that we'll be stepping through, so when you get into that course you should see a lot of the same familiar concepts that we are going to discuss today. There's also a nice link to model builder tips before you start here. It's not a bad place to start, giving a quick read about some tips and tricks for using the model builder in ArcGIS. So we're going to be working with a model builder. So coming up with some terminology and understanding some things we'll be talking about is important as we get started here. So the first thing we'll talk about are models. The term model, as used in a GIS, can have many meanings. Essentially, a model is an abstraction of reality that we use to represent either an object, a process, or some kind of event. So if you look at the middle image here, this is a model of a volcano. It's an abstract of reality. It's a representation of what a volcano looks like in a computer. So when you think about GIS, we are constantly modeling real-world things in our GIS, trying to represent reality in a digital format in the computer. So most of what we do in GIS is some level of modeling the real world, whether it be an object, like in this case, a single mountain showing elevations, or whether it be some kind of process where you're looking at maybe erosion of a trail in the national forest and trying to determine the types of soils and the steepness and the proximity to streams, and so you're modeling susceptibility of erosion a trail may have and its impacts on water quality depending on how close that trail is to a stream. So we model a lot of real-world things, processes, events, objects in a GIS. Models are used in all disciplines, in all work, in all parts of the world. We use models to better understand processes. So we may look at a model of how the heart works. If we're trying to fix a heart valve problem, doctors use models of organs to better understand organs. So it's an abstraction of reality, and we use models to better understand all kinds of processes beyond the GIS world. So models are real common. Maybe we look at the spread of some kind of virus using a model. Okay, so we look at models oftentimes. Other types of models, things like economic models. We try to model the economy and look at the effects of different policies on the economy. So we use models to look at what-if scenarios and to consider different things that may happen as a way to try to better understand some kind of process. So in ArcGIS, in the Esri world, a model is created using Model Builder, and this model is a collection of geoprocessing operations that allow us to visualize and automate an analysis workflow. So this discussion comes on the heels of our last discussion, which was on solving problems using GIS analysis. So we talked about analysis. Building a model helps us to visualize and automate some type of analysis. Models are used to plan and manage analyses from simple to complex. They become more valuable when you use them on more complex types of analyses. We had a short discussion last time on geoprocessing and analysis, and we said how all of the geoprocessing and analysis tools can be found in ArcToolbox, and how geoprocessing is processing of our geographic data. And key to the definition of geoprocessing is that you perform some operation on a data set, on a GIS layer, and it outputs a new data set. So you're not modifying the existing data set, you're applying some operation to a data set and outputting new data. So like the clip operation. The clip operation takes an input data source. We use roads of North Carolina as an example, the roads across the whole state. And you have a clip layer. In our case, we said that the clip layer is Buncombe County, one polygon. We can clip out the roads out of all of North Carolina based on the Buncombe County polygon. The new data set that's created would be just the roads in Buncombe County. Now, it doesn't affect the input data source, the roads of all of North Carolina. It doesn't do anything to that data source except for use it to create a new data source based on a clip layer. So don't get caught up on what is geoprocessing versus what's analysis. Some tools lean a little bit towards a geoprocessing tool, a tool that's just used to help manage our data, more of a data management thing than an analysis thing. In reality, the two, geoprocessing tools and analysis tools, are used hand in hand throughout an analysis process. So you don't really need to get too caught up on the difference between geoprocessing and analysis. And even if there is a difference, they blend together in how we do our work and perform analyses throughout all stages of the analytical process. So the model builder in these models. The model builder is an actual component of ArcGIS Desktop. It's a visual programming language, a language that enables you to create a program without writing code. So what does that mean? Well, usually when we automate processes in a computer environment, we have to write a program to do that. So outside of the GIS world, programmers have many roles and do a lot of things in the computer field. But one of the things they do a lot of is write little programs to automate processes. So our network administrator here at the school, he writes programs to push out updates and different modifications and customizations to the labs so that he doesn't have to go around and touch every single computer. He don't want to go around and double click here and go to here and open the disk management tool and do whatever he's doing. He don't want to have to go do that to 100 computers where he's got like a 10-step process. So he writes a program that automates that process. Right? So the same is true in the GIS world. A lot of things we do take a lot of steps to do and could be automated some. The model builder allows us to automate things, and it allows us to do it without writing code by hand. A common programming language used in the GIS field is Python, and these models can actually export out the actual Python code to code that could then be customized by a programmer. So they're a way of automating and documenting and writing tools that you don't have to be a programmer to do it. So you create programs in Model Builder by adding data and tool elements to the model and then connecting them to form some kind of workflow. So we've got data that can be stored in your geodatabases or shape files, and then we've got a lot of tools. We've started seeing the tools. They're all in Arc Toolbox. So all of the tools that are available in Arc Toolbox can be used in a model within Model Builder. It is a built-in application in ArcGIS, and it's designed to create reusable and shareable geoprocessing and analysis workflows. So it's important to understand that these things can be reused and they can be shared. So let's just look at a couple quick examples. The example on the left here is a model that loops through all of the feature classes in a geodatabase. It uses a special tool called an iterator or an iterate feature tool, and it projects each feature class to a new coordinate system. So we're not talking about the project on the fly functionality in ArcMap here. We've seen how if layers, feature classes, or shapefiles have a defined coordinate system, they can project on the fly in ArcMap to match something else. And that's all good and fine, and it's nice that layers will project on the fly. But I also emphasized during our coordinate systems discussion a couple of modules back that oftentimes we want our project data to all be in the same coordinate system. So what if someone gave you a data set or gave you a geodatabase, and let's just say it had 35 layers in it, 35 feature classes in it. All of those feature classes were in UTM. You wanted to project every one of those to state plane. The project tool takes an input data set and it projects it to a new data set in a new coordinate system. It creates new data, new layers. So if you had 30 some odd layers in a geodatabase, feature classes in a geodatabase, and you needed to project those 30 plus to a new coordinate system, you'd have to open the tool 30 plus times. You'd have to pick the input data source and pick the output data source 30 something times. It would take some time. This tool, you can point it at all the feature classes in this model that has been built. You can point it to all the feature classes in a geodatabase, and it'll just run through them, loop through each one, and output a new one. So it's a way to automate a process. This particular model isn't so much an analysis kind of thing. It's more of a data management tool. All right. Now the model on the right is more of a spatial analysis model. This model uses Spatial Analyst, which is an extension to ArcMap. Spatial Analyst has to be purchased and licensed in addition to ArcGIS Desktop. Its main use is to analyze raster data. So in this case, this is a site suitability example for a ski resort. So someone wants to locate a new ski resort and they're trying to decide the best place to put it. Now, when we work with raster data in site suitability, we often reclassify the data. And just as an example, let's look at some of these layers. Ownership, for example. Ownership of land could be a private owner, it could be a commercial type ownership, it could be a government ownership. So these different types of ownerships, you could rank them. The easiest and best ownership to possibly purchase is 1, and the worst is 10. So let's say private land, you rank 1, and then let's say commercial industrial sites, you rank 10. Because some strip mall shopping center you're probably not going to be able to purchase, or you're not going to put a ski resort there. Same for land cover. Some land cover types are more desirable for putting in a ski resort than others. So you rank them 1 to 10. Same with soil. Some soil types are better. Rank them 1 to 10. Same with travel. Travel, you end up doing a distance function where you say, you know, the places that are closest to a big city are better than places that are farther away. So you can see all of these they have different information in them, but if you reclassify them on the same scale, then you can put them together to show you the best areas. Slope is important when you're finding ski resorts, as well as the direction the slope faces. And this is called input sun, and then you reclassify the sun. Ski slopes, you do not want to be on south-facing slopes. South-facing slopes point towards the sun most of the time. So ski slopes are generally in a north-facing area. So you run through this. If you notice, there's 8 different layers. That's 8 reclassifies. It comes up with a new layer. Then you can weight them. Maybe some variables are more important than others. Maybe ownership is the most important thing. And so you end up running through this model, and it reclassifies 8 layers. It weights a bunch of them, and it smashes them all together to make to show you the areas that are most suitable based on your criteria. This is a little bit more of a complex model, and looking at it, you can kind of start to realize that running each one of these one after another starts to take a lot of time. And then when you get to the end, if you realize, oh, I should have reclassified ownership a different way. You know, I said that federal land was undesirable, and then I came to learn that actually a lot of ski resorts are on Forest Service land. They lease it from the Forest Service. So some ski resorts are actually on government-owned land. So maybe I reclassified that wrong. So I need to reclassify that one again to make Forest Service land more suitable than I did the first time. If it's in a model, you can change that one layer and then rerun the model, and you don't have to do each one of these things over and over again. It automates the process. It reduces error. If you went through and had to do all these steps over again, you would likely maybe make a mistake in one of the steps. And it also provides some documentation for what you're doing as well. So these are just two examples of models. So why create a model? I think I've covered some of these, but we'll just step through them. To see a visual representation of the analysis and geoprocessing operations. It helps you to better understand what you're doing. In our last class, we talked about creating workflow diagrams, how you can sketch out your analysis workflow. These build that analysis workflow for you. So it's a good documentation, a way to visualize what you're doing. You can automate and manage geoprocessing workflows. You can run complex successions of processes as a single tool. You can plug in additional tools and parameters as you need. Maybe you run the model and you realize you needed a whole other tool in there somewhere. You can also share your geoprocessing workflows with others by sending them the model you've created in Model Builder. So there's a lot of models you can download to do things, and the Esri website has some of these. They extend the functionality of the software a little bit. So a good example of a model that we can download is a model that creates a shaded relief model of a mountain. Okay, and let's just look at it real quick so I can describe to you a little bit better what it does. It's called a Swiss method of creating hill shades or shaded relief models. And so I'm going to bring up ArcGIS here, and we're going to look at a digital elevation model for Buncombe County. I showed this to you early in this class, probably the first day of class I showed some of this data. So if I go to add data, I've got a Buncombe County digital elevation model. And this is what Buncombe County looks like. This is a raster-based data set. Each pixel has a value for the elevation of it. And so the light areas are higher elevation, the dark areas are lower elevation. That's the French Broad River flowing through Asheville down there at the lowest points of the county. So the analysis tool I want to show you are in the Spatial Analyst toolbox, and under Surface is a Hillshade tool. Now notice these tools generate different types of surfaces. If you have a digital elevation model as an input, raster data set, using the Spatial Analyst tools, you could generate an aspect model. Aspect will show you what direction each cell faces. Is it a north-facing cell or slope, or a southeast-facing cell or slope? So you can generate an aspect model. You could generate contours and some other contour-related things. You can do a hillshade, which is a shaded relief model. We're going to look at that. You can do slope. How steep is a slope? Buncombe County has a steep slope ordinance that you can't build on a certain steepness slope above a certain elevation. So you could use this tool to look at that kind of thing. Viewshed, you could put in the location of like a cell phone tower and pick a point on this map, and it would show you everywhere that point could be seen from. So back in the early days of cell phone towers, we did a lot of that in GIS. When they wanted to put a new cell phone tower in, everybody was all concerned about seeing a new cell phone tower, and no one wanted a new cell phone tower. But nowadays, that's not quite as big a deal because we see them everywhere. Most people couldn't tell you how close the closest one is to them, even though they look at it every day. Subconsciously don't even know it's there hardly anymore. So viewshed analyses are important. One of the first analysis I did in graduate school was looked at a scenic Highway 11 in upstate South Carolina. There was a conservation group looking to buy properties of land along Highway 11. And so we did a viewshed analysis from the highway to show all the areas that you could see from the road. because they wanted to focus their efforts on buying a piece of land that you could see from the road. They didn't want it to be down on the other side of a mountain, so that at least allowed them to narrow down what they'd look at. So these tools, I like showing them for a couple of reasons. I'm slowly getting to my point about downloading a model using the Swiss Hillshade method from Esri, but most of these tools in here, they actually perform analysis on a raster data set. You go from a digital elevation model to a slope model, a digital elevation model to a hillshade model. You're performing analysis with these tools. And so this is how the hillshades work. When you create a hillshade, you input the digital elevation model. It's going to create an output raster. It's going to put it here in this default geodatabase. Remember that default geodatabase. We're going to discuss it again in a few slides in our Google Slides presentation. But it's under my username in my Documents folder, ArcGIS, this default geodatabase. I'm just going to let this file go there because it's kind of a temporary demo file for this class. Azimuth and altitude. So how do these things work? You can look at the tool help. The tool help will show you what this thing does. But essentially, the azimuth starts north is 0, and then it goes around clockwise back to 360. Okay, so the azimuth is the direction the sun's shining from. In this case, it would be shining from the northwest of us looking down. The altitude is the degree above the horizon the sun is at. So what this does is it creates a shaded relief model that depicts the landscape using light and shade, how light would reflect off the landscape and create shadows. Okay, so if we click OK, while that thing runs, I'm going to load in the hillshade I've already created and show you what it looks like. That's what it looks like. A lot of people see these and they think this is elevation. That's not elevation. Though the cells in this, see those pixelated cells? The value of these cells is a reflectance value of the sun. Okay, it's a gray shade. So you can see from looking at it, the sun is up here shining down this way because you can see the shadows on this side of the mountains. Right? So, back to this downloadable model from Esri. You can download a model that makes what's called a Swiss hillshade methodology. And what they do is they generate 4 different hillshades varying the sun, and then they smash them all together, varying where the sun is in the sky and altitude and azimuth, and then they smash them together, and it reduces getting these really dark areas like this that are kind of hard to interpret. I mean, this looks pretty good like it is, but you'd be amazed how much better it can be if you add to your analysis to create several of them and then put them together. So this model you can download from Esri does all that for you. You have to input the data sources to it, but it's got all the parameters set for the altitude and the azimuth of each one and how they get put together and how they're generated and all that stuff. So that's just one example. Shaded relief models are very visually appealing kind of things. We like to show them in maps. I usually demonstrate this with students and show them how you can also overlap the digital elevation model, which is this, on top of your hillshade. And if you go into the properties of your digital elevation model, you can show your elevation model using colors instead of a grayscale. And if we apply that, you'll see that it starts to have a little more colorful look. And then you could go in and you could, under the display tab, make it transparent a little bit. And you can start to show some of the shaded relief through it. And that starts to have a pretty nice effect on your map. Now this hillshade was really made for for like the high Sierras in California where there's snow on the mountains. There's not really snow on the mountains here, so a little trick I like to do here is under the symbology, I like to take it off of standard deviations and tell it to show the minimum and maximum based on the values in the grid, the digital elevation model. And instead of having the whites be up here at the 6373, I'm going to change that to 7,000. And so now the white is going to show the values at 7,000, which there are none. So it pushes the white off of the model. And it starts to look like that. Then you can modify this one too to separate it out a little bit more. But you get a pretty nice effect there doing things like that. So just a little bit of work with raster-based data, and you know, that's some simple analysis right there, modeling landscape and topography, not complex analysis techniques. But as you start to build shaded relief models that take into account many different hill shades, that it starts to become more complex. Okay, back to our presentation. So in Model Builder, you add data and elements to your model, and then you collect them into some kind of processing or analysis workflows. There's three basic types of elements that you can add to a model. They're variables. These are values in a model that might change, such as the input data or some parameter for a tool like buffer distance, or a query expression, a SQL, structured query language, some query expression, something you may change in the model that might change. You might not change it. It could change based on another tool. So you have variables. You can also have tools. These are the geoprocessing and analysis tools from ArcToolbox. All of those tools in ArcToolbox you can use in your models. Then you have connectors. You have simple data connectors. They're the most common type of connector. You have environment settings, preconditions, and feedbacks. In any given situation, you'll have variables and tools, but the types of connectors may change. So you may not have every bit of this, but you'll have a lot of these elements. Here's a little diagram that shows some of these. Your variables can be data variables and value variables, and they can either be input or derived on both of those. Your tools can be built-in tools to the software, and they can have things like iterators or model-only tools. Your tools can also be script tools, which are customized tools built by a user, or model tools, tools that are used in some other model can be put into another model. And then you have connectors, and we'll get to the data and environment more coming up, and precondition and feedback we don't use much in this class. So, model states. When you open up a model and you look at it, if it has no colors to it, if it looks like this, it is not ready to be run. They're not ready to be run when maybe a tool parameter isn't set, or maybe input data is incomplete, corrupt, or has some other problem. So a real common problem you'll see is you added the buffer tool to a model, but you didn't give it a buffer distance. You didn't put in some parameter the tool needs. Other times, maybe the input data is missing for some reason. And we're going to see a couple of ways that models can break when we look at some of the exercise data in the class. If you see your model elements displayed in color, they're ready to be run. The parameters for these elements have all been properly set. That buffer tool has a buffer distance, it's got some input data and some output data, and it's all set up and ready to run. So if you see the colors, they're ready to go. If you see drop shadows, see these gray drop shadows, that means the tool has already been run. All right, so those are the three model states: not ready to be run, ready to be run, and already run. All right, so how about these other settings, these model environment settings? So environment settings in the software are additional parameters you can set before running a tool. So there's settings that you can set that specify how the tool works. For example, you might want to set up an output geodatabase for running several tools, or set a cell size for the analysis output of a raster dataset. So, the output geodatabase. Well, let's just talk about defaults, period. Everything's got a default in the software. Something that it does without you, if you don't change it, it's going to do something. And the example, a good one, is the output geodatabase. What happens, where does a tool put the output data if you don't tell it to put it somewhere else? It puts it in this default geodatabase that's in your username. That thing gets built in when the software gets installed. So, what I usually do, I almost always have a default, I almost always have a geodatabase specific to the project I'm working on. For example, if I'm working on a Buncombe County project, I've probably got a Buncombe County geodatabase. And so, in your map document, under the map document properties, you can change your default geodatabase from that default geodatabase to one for your project. And I often do this. I come into my database and I go, and let's just say, alright, so now this Asheville geodatabase, and you can't see it because it streams off through here. My default geodatabase is Asheville now. And this isn't saved, so I don't know if that might not work until I save my map. But essentially what it should do is make any output go to that database. Okay? See what that did? So when you're working on a project for, say, Buncombe County or for Asheville, every new data set that gets created, you don't want to have to change it from that default geodatabase to this Asheville geodatabase. So you can change that at the program level, at the application level. You can also change it in the model. Okay? So there's settings. There's settings that change the default operation. You can change it to something more suitable. For instance, another example, the hillshade. When you run the hillshade, the default operation is the output layer, the cell size that gets created, the resolution of the raster dataset is going to be the same as the input dataset. Maybe you want to reduce the resolution. So you could change that environment setting so it doesn't happen. Alright. So, those are environment settings. It's important to understand that these environment settings can be set in different places. At the application level, they can be set. You can then also set them at the tool level. And if you set one at the tool level, it's going to override what's set at the application. Then down at the model, if you add a tool to a model, but in the model you want that tool to behave differently than its default operation and in its tool, you can change the setting at the model level. You can also change it at the model process level. So the finer control you have over it down the level overrides everything above it. Now, remember that there are default settings for all this stuff. And there's a lot to know about every tool in ArcToolbox. And a lot of times you get in there and you start reading about it and you get overwhelmed and you just say, I'm just going to run it and take the defaults. That's okay. You want to make every effort to really understand the tool you're running. You want to read the help. You want to understand it as good as you can. But at some point, sometimes you just got to run a tool and see what it does, and then maybe realize that, oh, that's what that setting was doing. You didn't quite get the output you expected. So don't feel like you have to go in the environment settings and tweak every setting in there. If you don't go in there at all, the tool will typically run. It just might not give you the output you might be expecting. So planning your analysis is important. These are some questions you should consider before building your model. If you think back to our spatial analysis, solving problems with spatial analysis discussion from last week, We talked about the geographic inquiry process, where you ask a question and then you look for data, and it's a cyclical process. It's a way to approach a problem using geographic information. That is very similar to this. Try to plan and think through what you're doing. Think about the goal of your model or the goal of your analysis. Think about what you're trying to do. Think about what data is required. If you need to purchase some or build some, or if you have the data, think about the most effective workflow to achieve your goals. Now, a lot of these things aren't overly obvious, especially when you're just trying to figure out how to do an analysis, but at least giving it some thought, you'll stave off some problems that you might run into if you don't plan at all. So think about the scenario and criteria for your analysis and set goals. Explore and gather necessary data that might involve creating or modifying and editing data. Choose the tools that will enable you to achieve your goals. And again, this requires a thorough understanding of your goals and the tools you'll use. You've got to investigate and research the tools to at least get a basic understanding of them. When I first started using GIS, every time they sent the software out, they sent us a bookshelf worth of manuals, paper manuals, literally a bookshelf worth. And we would, every single day, we'd be in the lab with those books pulled out, flipping through, reading about the commands, trying to understand what they did. These days, we do most of that by looking at the software help, but you want to take the time to try to understand the tools and what they're doing. You want to build and run your model next. By this time, you should have determined everything you need in your model. There's always time to tweak the model. Don't be hard on yourself if you forgot something. Be hard on yourself if you didn't try to plan at all and forgot a lot of things. Plan as much as you can and then adapt as you need. After that, you want to explore and refine the results of your model. You might view, analyze, and symbolize your results to determine if they're satisfactory, and I don't mean whether they got the results you want. Maybe you got the wrong results, but you think they're correct. Wait, maybe you got the results you didn't necessarily want, but they are correct. So you can always run the model again with different tool inputs or different parameters if you need as well. So make sure to consider that. Having a model allows you to tweak some small settings and then rerun it and not have to run it all individually. Another great part about models is that they allow you to better manage intermediate data. So we discussed intermediate data also last class or 2 classes ago briefly. We said that a lot of GIS tools, geoprocessing tools, analysis tools, build data sets that are just used to input to the next stage in your process. They're used to create something else, but they're not needed at the end. They're intermediate data sets. And they're one of the reasons that we end up with so much data in the GIS world is a lot of times people don't go through and delete intermediate data sets. If you keep intermediate data sets and something goes wrong at a later stage in your analysis workflow, you can just step back one step to that intermediate data set. So people are slow to delete those intermediate data sets so they don't have to go back to the beginning and start all over if something breaks. Models allow you to automatically delete those intermediate data sets. And since you've got a model, you don't have to go through and step through the whole process. You just run the model and it goes through the whole process. So intermediate data is managed well with models. I've probably got 100 gigabytes of data that I could delete. They're all intermediate data sets that I got created, trying a new tool with some new parameters, changing my azimuth on a hillshade from 315 to 275 and tweaking the altitude to see what effects you get. Next thing you know, you've got 15 different hillshades you created, trying these different parameters, and maybe you didn't name them really well, and you're afraid to delete them. You might need them. So intermediate data, whether it's intermediate data or just demo data, you were trying some new parameters in a tool, you end up with a lot of data that you don't necessarily need. So intermediate data with models is managed well. Validate and running your model. Validating a model identifies problems with the model. It helps you to identify incorrect parameters, non-existent data, or improper variables for a specific tool. We're going to look at this as well. It's also valuable to document your model. Documenting it enables you and others to understand it more easily at a later date. Think of a document, documenting your model as metadata for your model. This is data about your model, how it works, why it works. You can add labels to the model itself that show workflow and describe particular tools and data elements and processes. So you can do it down to the process level in a model. I've provided models with databases to clients in the past, and the less I've documented them when I handed it over to the client meant the more emails and phone calls I was going to have to answer after it was delivered. So the better you document something, the better you can use it later, and the better someone else can use it. All right, so let's look at the class data, and I'm going to point out a couple of problems that occur. So the Esri Virtual Campus, when you download the data and you go to work with the data, I'm going to create a new map here. I'm not going to save this. All right. So I connected to my data folder here on the U drive, which is a storage space that I have access to. It's a server here. I've got a documents folder with my Esri training and my building models folder in it. Now that is important to recognize where my data is right there. Okay. Now notice that these sets of tools can be stored in a geodatabase. They look a lot like the tools in a in Arc Toolbox. So these tools, you can create new custom tool sets. You can save them in Arc Toolbox or in a geodatabase or in a folder somewhere. So you can organize a set of tools wherever you want. And a lot of times we put tools in a geodatabase just so they're all coupled with the data and everything else. You can even, so this is a model in this tool set, but I could even just copy I could copy this delete features tool and put it in that tool set. So you can copy existing tools and put them in there too. So you can store these tools, tool sets, geoprocessing tools in different places. Now this model, you edit it by right clicking and going to edit. And here the model opens in this window. It's a little bit off the screen. I'm going to double click. You can zoom in and out on the model. You can zoom it to the full extent. You can have it auto layout. Let's zoom to the full extent so you can see everything. I think I actually want to zoom in here a little bit. Is this model to be ready to be run or not? Some of it's already been run, right? And some of it's not ready to be run. So what's going on here? It's kind of weird. So when you see something like this, remember what we said. When I see this buffer tool right there, all white, I think a couple things. Either it doesn't have a buffer distance, or for some reason maybe the input data, it doesn't see the input data or the output data, or I don't know what's going on with it. In the exercise, they have you come in here, double click that, and give it its appropriate buffer distance. But unfortunately, that still doesn't fix it. If you look at the buffer tool here, by double clicking it, it's got some input features, and then it creates an output feature class. The buffer tool is a geoprocessing tool. It creates this output feature class. It tries to put that output feature class in the Fort Pierce geodatabase that's in the building models folder, that's in the Esri training folder on my C drive. That folder does not exist on my C drive. I put my data somewhere else. That's hard coded into this model. And so if you put your data somewhere other than where the default extraction is, then that's a problem. This file gets created, this feature class, so I'm going to select it and I'm going to copy it because I want to name it the same thing they were going to call it. And I'm going to move it over. I'm going to tell it to put it in where my Fort Pierce geodatabase is. Okay, I'm going to paste the name here. I did that just so I made sure to get the exact same name. So I click Save, and I click OK. Darn, that still didn't fix it. Why not? It didn't fix it because it doesn't have a linear distance. And so we could have fixed it there, or we could fix it here. If you're getting this Windows security warning, just keep clicking yes to it. I think it's coming up because of a Windows update. I've been seeing it on every machine I sit at, and all the students have been saying they see it. I used to see it a couple years ago. It was there too, and it comes and it goes. Just keep clicking yes. I don't remember what they tell us to put the buffer distance in there, and that didn't fix it. Yeah, it did. Okay, boom, it's ready to be run now. So that buffer distance you need to, the exercise tells you to put in. The other problem is kind of unexpected, but it's good for learning how this stuff works. So pay attention to those kind of things to fix your models to be run. If you fix what it tells you to in the course and it still doesn't work, you'll want to do those things to get it fixed. Okay. All right. That's most of what I have, I believe, for this discussion. You can have the rest of the class to work on your lab.